My name is Reza Shokri, and this is a joint work with my colleagues at Cornell Tech on how to reason quantitatively about privacy in machine learning. Machine learning is the electricity of new technologies, and it plays a very important role in many services in the internet. Because it's very useful, and for its wide applications, it has been provided as a service by Google, Amazon, Microsoft, and many others. In such services, the service provider gives you a training API through which you upload the data to the cloud and ask for training a model, for example, a classification model. And later on, when you want to use the model, you can query the model using a prediction API and ask for predictions. For example, to ask for classifying an unlabeled image, as I show in this slide. The prediction is a vector of probabilities that assigns a probability to each class. Here I show these probabilities in an abstract form using the length of these bars. So you send an image of a car and get the probability of whether this is an airplane, automobile, ship, truck, and so on. This is a very good example of black box training and access to a machine learning model. The model remains in the cloud. The user does not have direct access to it, does not know the type and architecture of the model, does not know the parameters of the model, cannot download the model, but can only indirectly benefit from it through the prediction API. And when ask for prediction, it has no observation on the intermediate steps of doing that prediction either. This is very useful for many applications. For example, if you want to build a new mobile app and want to benefit from it, you have some data, you want to build a machine learning model, you use this service. Later on, by single function call, you can label the data that you receive later on. And you will be charged based on the number of queries that you ask for predictions. This is very useful, but when I look at this, I ask the question of whether these frameworks, and in general machine learning models, leak information about their training data. Note that at the time that you ask for predictions, the data is gone. You're interacting with a model that was previously trained on some data that could have been sensitive. So is there any leakage about the data through the model? To answer this, we study information leakage through the eyes of an attack, a particular inference attack which is known as membership inference attack. The question here is whether an attacker who used the model can learn whether a particular record was part of the training data or not. So the attacker sends a query, gets predictions on that query, and wants to know whether that data that was in the input query was part of the training set or not. You admit that if an attacker is successful in such attack, it indicates that there is a significant amount of information leakage about the training data. Membership inference attack is not new to the privacy domain and is not exclusive to machine learning. It has been studied by researchers on releasing summary statistics on data sets. So consider, for example, you have a data set and the average value of each attribute is released. The attacker, by observing this summary statistics, wants to know whether a particular record was part of the data set. And the assumption is that the attacker has some information about the underlying distribution of the data, or, for example, has some data samples from the same distribution. And what the attacker does is to use some reference data that is assumed to be sampled from the underlying population and runs a statistical test to find out whether the target data record is more similar to to the statistics computed from the reference data compared to the statistics that is released as summary statistics. In the case of running membership inference attack on machine learning models, the problem is much more challenging because we don't have a direct function that is computed on the data. As I explained before, we have this indirect access to the data. In the case of black box setting, the setting is much more challenging because we have no knowledge about the parameters of the model, we have no access to the internal computations of the model, and we might not have much knowledge or even no knowledge about the underlying distribution of the training data. So how can we go about exploiting the model's predictions and find the members of the training data? The main insight to our attack, the main intuition of our attack, is that machine learning models tend to behave differently with respect to their training data compared to the data they haven't seen. And this exhibits itself in the phenomenon known as overfitting, where the accuracy on the training data is much larger than the prediction accuracy on the test data. So I exploit this for the attack. Consider a hypothetical scenario through which I explain the intuitions of the attack and different steps of the attack. Suppose that I have access to the training data of the model that I'm attacking. If I query the model with that data, get the predictions, I get some probability vectors, right? Some classifications for different classes. Suppose that I have some data also outside the training data, that I query the model and get some classifications of that data. The only thing that I need to do now is to find a way to recognize the difference between these two prediction vectors, these two distributions. One distribution that is coming from the data inside the training set, and one distribution that reflects the predictions on the data that is outside the training set. So what algorithm should I use for this purpose? The method that we use here is called machine learning. Machine learning is exactly what we want to do. We want to train a model, an attack model, that observes the prediction vector and outputs the probability that this prediction vector is coming from the members versus the non-members. So it's a binary classifier. The main question and the big challenge here is that how can I train such an attack model without having access to the training data of the target model? Note that the main goal of this attack model is to learn the behavior of the target model with respect to its training data compared to the data outside the training set. So our idea to train an attack model without having access to the training data is to learn that behavior not from the target model, but from some other models that we call shadow models. Assume that we know the type and architecture of the target model, and assume that we have some data that is sampled from the same underlying distribution as the training data of the target model. We can train some models we call shadow models, and we train the attack model on the predictions that these shadow models produce on their training data versus their test data. If the type and architecture of these models is the same as the type and architecture of the target model, and of course their parameters are different, and if the data on which they are trained is similar to the data that the target model was trained, then the behavior of these models with respect to their test and train is similar to the behavior of the target model with respect to its own test and train. Well, the question is, how can we know the architecture and type of the shadow models, specifically in the black box setting of machine learning as a service, where we have no idea what, or little idea, what they train? And to overcome this practical challenge, basically it's easy to notice that the attacker also has access to the same platform as the user who trained the target model. So I can create an account and just ask Google, for example, to train some models for me. And if I ask for the same classification model same classification task for similar type of data, there is no reason why Google trains a dramatically different model. So these shadow models are of the same type and architecture as the target models. The next challenge is, where can I get the data to train the shadow models? Well, in the simpler case, if I know the type of data that was used to train the target model, then I can also go and collect some real data, which is of the same type, and train my shadow models. Say, for example, if the target model was trained on some genomic data, then I can go and collect some other genomic data and train the shadow models on that. But in the harder case, a more realistic case, I might not have much knowledge about the type of the data or the features that were collected for training the target model. In this case, we suggest to synthesize data for training the shadow models. If you want to synthesize data, you need to have some score function that tells you how good synthetic data is. And in our case, we have a very good oracle that could help us to build that score function, and that oracle is the prediction API. Our intuition is that if the model is very confident in its prediction on some sample input data, this is a good indication that that data is similar to the data that was used for training the model. And we use a search algorithm to find those high confidence input data. You can use different search algorithms. We use a simple hill climbing algorithm where we start from some random record, and then each iteration we change some of the features of the data, and we move towards the area where the prediction confidence is higher and higher, where we then keep the high confident records. So if you look at the overall framework that we have here, we have access to a model through a prediction API. We use that to synthesize some data. We generate a lot of data, as much as we want, using this algorithm for synthesizing data. Then we train as many shadow models as we want on that data using the same platform. Then we query the shadow models with their own test and train data, and we generate labeled data for the attack model, and we train the attack model. And at the time that we want to use the attack, when we want to know whether a particular single data record was part of the training set of the target model, we query the target model with that target record. We get the classification, the prediction vector, we pass it to the attack model, and it gives us the probability of membership of that record. We use this methodology to evaluate privacy of many models that we train locally, as well as the models that were trained by Google and Amazon. Here I show the results of our attack on Google Machine Learning as a Service. You can find the results of the other attacks in the paper. The data set that we have here is obtained from a Kaggle competition for classifying customers. The features are binary and indicate whether a customer has purchased a particular item or not. The total number of classes is 100. This plot shows the distribution of the accuracy of the membership inference attack over different classes. So if you look at one point in this plot, it shows the cumulative fraction of classes on the y-axis for which the attacker can obtain a membership inference precision up to certain value on the x-axis. So I can tell you that if you train shadow models on real data for almost all the classes, the inference precision of the attack is above 0.8. The overall accuracy across all the classes in this case is 0.93, which means that if the attacker labels a prediction, a record, as member or non-member in 93% of the cases, he's correct. These accuracies drop a little bit when we train the shadow models on synthetic data. And the reason for this is that the quality of the synthetic data that we generate is not the same for all the classes. So for some classes, the model produces some poor quality data that we use for training the shadow models. I want to reiterate here that we get this accuracy without knowing the training algorithm, without knowing the model type and architecture, without having access to the parameters of the model. And in the case of training the shadow model on synthetic data, we don't even know the data distribution. And despite all these limitations and limited amount of knowledge, the attacker can get up to this 90% accuracy of finding out which records are member of the training set and which ones are not. Of course, this does not mean that for all models and all types of data, we can get accuracy up to this level, because this metric shows how much information could be leaked for this platform, and could be compared with the amount of information that could be leaked from other platforms. And of course, if the model is privacy preserving and is trained in a privacy preserving manner, it should be secure and robust against these attacks. Let's look at the big picture here. When we train a model, we have a data universe. We have some samples from that data universe that we use to train a model. And there are two big objectives here: the privacy objective and the learning objective. The main question with respect to the privacy of the model is whether the model leaks information about the data in the training sets. And the main question with respect to the learning is whether the model generalized to data outside the training set. So what do you think about these two objectives? They're pretty similar. They're very consistent with each other. In fact, overfitting is the common enemy of the two. If a model is overfitted, it's not going to generalize to the data outside the training set, and is going to leak a lot of information about the training data. This is very promising because for the first time in the history of data privacy, the utility and privacy are not in a direct conflict with each other. In fact, it is possible to train models that are utility preserving and at the same time satisfy privacy requirements. So let me conclude my talk with this optimistic message. Thanks.